Okay, I'm going to start this video by showing you what some of the instruments we're going to be learning about look like. This little guy here is called a UV-Vis spectrophotometer. We'll learn about that one first, and then we'll eventually learn about its larger cousin, the atomic spectrometer. What we won't learn about is just how crazy these spectrometers can get. For example, this is the instrument that I used in graduate school. You can see how I felt about it here. It's actually at a very neat facility called the Advanced Light Source over in California, where an enormous amount of X-rays are produced in this ring here, which is actually a rather large particle accelerator known as a synchrotron. And I once calculated how long it would take to absorb a lethal dose of radiation if you were to be inside of that ring. It came out to be about 1 nanosecond, or in 1 second you would absorb enough radiation to kill 1 billion people. So that's how many X-rays are going through there. And these are the kinds of thoughts we have at 4 a.m. after a week of all-nighters doing research. Me with hair. What a concept. But no matter how complicated these instruments are, there are certain basic commonalities that they all have, which are represented in the schematic here. It starts with a light source that produces a range of different wavelengths, which I'm trying to represent with different colors. We then use a device known as a monochromator to select a particular wavelength of light and direct only that into our sample. We'll cover what that PO means and this P over here momentarily. The light then travels through some length of sample, and we call that length the path length. It's usually defined by the length of the container that our solution is inside of. In our first experiments we learn about, these containers are called cuvettes, although in other spectroscopies we don't necessarily use them. If this light has an energy that is equal to the delta E between energy levels of our sample, then based on that rule we learned earlier, some of this light can be absorbed by the chemicals, and thus less of it comes out the other side. But on that other side we have a detector which measures how much light reaches it. And then that detector is connected to a computer, which displays our data. So let's get into what's going on here and make some notes. We'll call this section Absorption of Light. Absorption of light. A spectrophotometer actually measures how much light is transmitted through a sample. So we're going to write down spectrophotometer measures transmission of light. Spectrophotometer measures transmission of light. So to take a piece from that schematic on the previous slide, let's just draw a cuvette that contains some chemical of interest, and let's say we shine some intensity of light into the sample, which we will represent with P for power, which we'll recall from electrochemistry relates to energy, and we've already discussed that light has an energy. And then we'll put a little O subscript to indicate that this is the original power of light going through, and if some of that is absorbed by the sample, then less will come out the other side, and we'll label that power of light just P, and we have a detector that measures that light. And presumably the instrument knows how much light was being shined in the first place. So in this simple diagram we could say 4 light waves or light photons were directed into the sample, only 3 made it out, so 1/4 of the light was absorbed. So we can back calculate how much light is absorbed by first determining how much is transmitted and makes it to this detector. So let's write down some terms and formulas, starting with transmittance, since that's what we're ultimately measuring. So T for transmittance, which is just the fraction of light that makes it out to that detector compared to the original power of light that reached the sample. So P for power of light exiting sample. Power of light exiting sample. And the units for power in this context are a little bit different than what we learned in electrochemistry. Instead of just joules per second, it's actually joules per second times CM squared. So we have this area term in there. And so really what these units are describing is how much energy is reaching a given area of a sample per second. And energy is the most important part because energy is related to light. And so the more energy that reaches an area of the sample in a given unit of time, the more light must be reaching the sample. So all of this is to say that the larger the power, the more light must be reaching the sample. And the lower the power that comes out the other side, the more light must have been absorbed by our sample. And we'll see later that that's a very important concept for analytical chemistry. But let's just finish off this definition. PO is the original power of light. Original power of light. And right now we've been talking about transmittance. We have the equation for it, but let's verbally define it. It's the fraction of light that passes through a sample. Fraction of light passing through a sample. Fraction of light passing through a sample. And sometimes, rather than expressing this as a fraction, we'll express it as a percentage, which we just call percent transmittance, and it's literally just taking that fraction and multiplying by 100%. But these are technically not the same thing. Make sure you understand the difference between those two terms, transmittance versus percent transmittance. As has been described earlier, the lower this value becomes, the smaller that fraction of light that makes it through a sample, the greater the amount of light that was absorbed by a sample. And so this brings us to the most important concept, absorbance, which just has the symbol A, although sometimes you'll see ABS, but we'll just use A. This is equal to the log of 1 over T. So there we can see our inverse relationship. Using some quick logarithmic math, we can rewrite this as negative log of just T. And let's be clear, this is transmittance, not percent transmittance. If you plug in percent transmittance into this equation, you'll get the wrong value. And this term we're calling absorbance varies linearly with concentration. Varies linearly with concentration. And this rule is known as Beer's law. Beer's law. And it's extremely important for analytical chemistry. We can already see the key term concentration, which relates to quantification. And so the rest of this video will be dedicated to the concept of Beer's law, although we'll get into the application later. Let me just get all of this out of the way. Now first I'm just going to write down the equation for Beer's law, and then we'll define all of these symbols. It starts with A for absorbance, equals epsilon, leave some space, times lowercase b, leave more space, times C. And I'm going to define these from right to left. So C stands for concentration, particularly concentration of the absorber chemical. So concentration absorber, unit is molarity like usual. The lowercase b stands for path length. How far does the light have to travel through the sample? In the first experiments we'll cover, this length is defined by the cuvette length, that container I showed earlier. Cuvette length. And the default unit is a centimeter, not meters. And finally, epsilon represents something called molar absorptivity. Molar absorptivity. For now, what we'll say is that this is related to the energy levels of a sample and is thus sample dependent. Related to energy levels, sample dependent. Sample dependent. Different chemicals have different orbitals at different energies. And so I wouldn't write this down, but just to make it clear what I'm saying, imagine one chemical has energy levels separated by this much, while another chemical has energy levels separated by a smaller energy difference. And so by our cardinal rule, where the energy of light that is absorbed is equal to the difference in energy between levels, we would say that the chemical that has these levels would absorb a lower energy light than the chemical that has these levels. And so that's what absorptivity is relating to. It's ultimately how well does a chemical absorb a particular energy of light. Hopefully this concept will make more sense as we get deeper into this topic, but for now I will direct your attention to the idea that absorbance varies linearly with all three of these terms. And so if we double any one of these, we double absorbance. Triple one, triple absorbance. So let's end with a visual designed to show why absorbance would vary in such a manner. First up, let's address concentration. The more absorbers there are in a given volume, the more chances that light will be absorbed. Makes sense. So imagine we have this cuvette at some low concentration of blue chemicals. We'll get into color later, but a blue chemical is most likely to absorb orange light. Well, now imagine that same cuvette contains twice as many of these absorbing blue chemicals. And so there's twice the chances for this orange light to be absorbed, and so less makes it out the other side. Absorbance doubles with double the concentration. Path length is also rather straightforward. The further the length that the light must travel, the more chances that the light will be absorbed. So now we have two different cuvettes with the same concentration. Notice that it's the same level of dispersion of these blue molecules. But because this length here is twice as long, there are once again double the chances of light interacting with one of these molecules and being absorbed. And finally, the least intuitive of the three, molar absorptivity. So here we have two different chemicals, one red, one blue, same concentration, same path length. But as we'll discuss in a future video, and as you may already know, a red chemical is going to absorb orange light far worse than a blue chemical. And thus the red chemical has a lower molar absorptivity than the blue chemical, and even though everything else is the same, the blue chemical just absorbs more light. So those are the fundamentals of Beer's law. We'll get into application later.